Okay, the purpose of this video is to describe how we can figure out the output of a linear time invariant system. In other words, the response of that linear time invariant system to an arbitrary input. In the process of doing this, we'll introduce the idea of an impulse response, and we'll introduce the idea of convolution. And to preview the result we'll get, the output, or the response of a linear time invariant system to an arbitrary input, is obtained as the convolution of that arbitrary input with the system's impulse response. This is a good thing because it turns out that convolution in the time domain, which is what we will derive by the end of this video, turns into multiplication in a frequency domain. So for a Laplace transform domain or a Fourier transform domain, which makes the analysis of linear time invariant systems much, much simpler than they otherwise would be. So let's begin by assuming that we have a system, and we're going to assume that this system is a linear time invariant system because we want all the magic that's going to occur in this video to occur. And rather than putting an arbitrary input x into it, we're going to put a delta function. And we're going to give a special name to the output of the system in response to the delta function. We're going to call it h of t. The delta function going in is an impulse because, in some sense, inputting a delta function to a system is like smacking it with a hammer if it's a physical system, or if you've got an electrical system, it's like applying a bolt of lightning. Impulses can instantaneously change position or velocity or the charge on a capacitor or the current through an inductor, which means that in real life they don't exist. But they're a useful abstraction. And the response of the system to the impulse, we're going to call its impulse response. Okay, and again, this impulse response we're going to call h of t. Okay, now eventually we want to be able to get the response of the system to an arbitrary input. The first step in doing that is to recall that because the system is time invariant, if I take a delta function of t minus a, where a is some number, in the past we've been using tau here in place of a, but now we're going to use a because in a minute we're going to use tau for something else. And by the time I'm done, I want everybody to be as confused as possible. So anyway, if I put a delta function shifted by an amount a in, I get the impulse response shifted by that same amount a at the output. That's because the system is time invariant. So this is one of the important things we're going to use. The next thing we're going to do, in a previous video, we talked about the idea that an arbitrary signal x of t can be written as the integral from minus infinity to infinity of x of tau delta of t minus tau d tau. Okay? And again, this is one of those things that may seem like a completely pointless thing to do, but it turns out to be very useful in our current approach, or in our current effort to find the output of a system due to an arbitrary input. Because what we've done is we've described this arbitrary input in terms of the arbitrary input and a shifted delta function. Now, we know that if we put a time-shifted delta function in to our LTI system, we get this time-shifted impulse response out. And so we're going to use the fact that the system is linear, and we've represented x of t here as essentially a linear combination of delta functions. And when I mean linear combination of delta functions, conceptually the idea is that an integral is the limit of a whole bunch of sums of things. And so in this case, I have the limit of the sums of delta functions times my input signal. Okay, so the idea then is that because I have a linear system, if I have an input, again, this is the input. Here, we'll even use a different color to underline it now. This is the input to my system, and this input is essentially the sum of a bunch of things that are x of tau times delta of t minus tau. Then the output is going to be essentially the sum of the outputs I would get in response to these inputs. And again, at this point, we can think of x of tau as being a constant in front of a delta of t minus tau, a shifted delta function. So my output can be written as the integral from minus infinity to infinity x of tau delta, whoops, we don't want delta. That's the wrong thing here. We want h of t minus tau d tau. Okay, so what I've done in this expression is replace the delta function going into the system, this guy, with h of t minus tau coming out of the system. And again, the x of taus stay the same because for each delta function, this x of tau is just like a constant out in front. Okay, this may seem like black magic or voodoo, and I apologize for that. Hopefully it will make sense at some point. So this integral, where I have x of tau times h of t minus tau, and I'm integrating from minus infinity to infinity, where tau is my variable of integration, this occurs often enough that we give it a special symbol. We write x of t, and then this is an asterisk or a star, y of t, and we give it a special name. This is a convolution integral. Okay. So what we have over here, this notation is just a shorthand for this whole integral expression. Okay. So the beautiful result that we have is that the output of a system is given by the convolution of the input. Whoops, and I did this wrong. Arg. Let's clean this one up, because if you get this wrong, you're in serious trouble. Okay, so the input times the impulse response. I don't know where that y came from earlier. Okay, so the output y is given by the convolution of the input and the impulse response. So what this says now is if I know the impulse response to a system, or of a system, then I can figure out the output of the system with if I put any given input into it by just working the convolution integral. That's the good news. The bad news is you may be looking at this convolution integral and saying, well, that doesn't look like it's necessarily going to be that much fun. And it turns out that indeed, for almost anything except some very simple examples, like the type we'll do in another video, working this convolution integral is very, very painful. And in fact, isn't done very often. So why do we care? Well, again, the primary reason for this to be a very useful result is that this convolution integral, again, this is in the time domain. I've got x of t and h of t, turns into a multiplication in a Laplace transform domain or a frequency domain. And that's extremely useful, and we use that all the time. So I think we'll stop there. We'll produce another video that shows you how to actually compute this convolution for one or two very simple cases. Oh, I guess one last comment. If you're not going to actually compute the convolution integral for most of the things you're going to do, why bother to know how to compute it? Well, that's actually a very good question. It turns out there's a couple reasons. One is that the ability to compute convolution integrals is seen as a sort of a macho thing in signal processing. If you can compute convoluted integrals, you're considered to be tough. Another reason is that there are places, especially when you're looking at Fourier transforms and figuring out properties of Fourier transforms, where the fact that convolution in the time domain turns into multiplication in the frequency domain and vice versa means that it's easy to compute Fourier transforms in certain situations if you can work a convolution integral. It also turns out, this is a continuous time convolution integral, there is a corresponding discrete time convolution sum, and it turns out that you use the convolution sum a lot when you're implementing digital signal processing algorithms. It's an algorithm that's very easy to implement on a computer, and in fact, they have specific digital signal processing architectures that are optimized to do this sort of convolution. And so for discrete time signals, which are the only kind you can actually run through a computer, the convolution sum, because it's a discrete time signal, is used all the time. Now it turns out that the computation is almost always done by a computer and not a person, so your ability as a person to compute this or to compute a convolution sum may not be all that important. So with that disclaimer, we'll close out this video.